So now that we have an idea of how to find the areas under a curve, basically is what we were doing in that last section, was finding areas under a curve of some kind. We want to actually kind of formalize this whole idea. And we're going to mention a thing called a definite integral. So a definite integral is if f is continuous on some closed interval from a to b, and you divide that interval from a to b into what we call n subintervals of equal width. And that width is that delta x equals b minus a over a. So you find the width of the interval and divide by how many intervals you want to have. And that gives you that, where a equals x0, and then you got an x1, and you're going to x2, and you're going to keep going until you get to xn, which is your b. These are the endpoints of the intervals. We can call these sample points. These are just points that are inside each of these intervals. So with x sub 1 star, x sub 2 star, all the way to x sub n star, with x sub I star is in the xi minus 1 to xi interval. This is kind of a formal thing, but just to let you know kind of what this is doing, then we can define this thing called a definite integral of f from a to b is this limit as n goes to infinity of the summation I equals 1 to n of f of x sub I star delta x. Remember, this was the area under the curve. This was that area we're looking for. So that's what that was. We actually formalize this and call this an integral. This summation symbol becomes this big giant looking S for summation. I guess you can think of it that way. It goes from A to B of your function f of x. And then the delta x becomes a dx, kind of like the dx's we did in derivatives. So it's very similar to that kind of concept. It's telling you what that change is. It's that change in x. By the way, this has been developed by many, many people. This actually was Leipzig's original notation, but he hadn't formalized it. This was more formalized by a man by the name of, well, lots of people did it, but a man by the name of Riemann did this piece. And so this is actually known as a Riemann sum. Because they did all these things. Just to let you know a couple other things, that f of x is, remember, if you think about under a radical, it's called the radicand. So we give names to these things. This is known as the integrand. The a and b are your limits of integration. A is your lower limit and b is your upper. Because these are just areas, that's all this is. This is just an area. We can think of this as, we want to look at this integral, this area here. So we're looking for this area from A here. This could be area 1, let's call it. And then over here to B, this would be your area 2. And then all we do is add these two areas together, and we can actually talk about that whole limit. So the integral from, let's say this is C here, from A to C of f of x, plus the integral from C to B of f of x dx. That would be that area. Notice that because we're adding these up together, we're adding up these rectangles underneath here. These rectangles are all going to have positive y values. So they're all going to be positive. So this integral here is going to be positive. So the integral from A to C of f of x is equal to the limit, by the way, as n goes to infinity, of the summation I equal 1 to n of f of xi star, we'll just call it fi xi delta x. Well, these function values are always positive. You add up a bunch of positive numbers, you're going to get a positive number back. If we do the other one from C to B of f of x dx, that's going to be the limit as n goes to infinity of the summation I equal 1 to n. And it's okay to call them the same i's because they're different processes here. Not processes, but you're going to do this one separate from this one, so it doesn't matter that they're both I. But these function values are all negative. So this is going to be negative. So your integrals can be negative and can be positive. This means that your actual total integral from a to b of f of x dx is going to be taking area 1 and subtracting off area 2, because you want them both to be positive. So the actual area, the total area, would be subtracting these two areas. I want to make sure you can see how to express these limits in terms of an integral. So we're going to express the limit as n goes to infinity of the summation I equal 1 to n of e to the xi over 1 plus xi delta x on the interval from 1 to 5 as an integral. So this would be as an integral. We're going to go from 1, so that's my lower limit, to 5, that's my upper limit. And then my function was e to the xi, so it's e to the x over top of 1 plus x, and then the delta x becomes dx. So there's your integral. We go to these summation notations because we actually know a bunch of the different sums. We actually can have some summation rules that tell us what the summation I equal 1 to n of I is. That means we're adding 1 plus 2 plus 3 plus 4 plus 5 to itself until we get to n. This was actually developed, I shouldn't say developed, this was actually found by a man by the name of Gauss when he was like 6. His teacher wanted him to just spend some time adding a bunch of numbers together from 1 to 100. And he did it really, really fast because he figured out all you have to do is take and add n and n plus 1 and then divide by 2. Gauss was a genius, by the way, so don't feel inferior. I can't do that either. But if you think about it, at least I couldn't at 6. What you're doing is, let's say I want to add 1 to 10, then I'm taking 10 times 11 and dividing by 2. And 10 times 11 is 110, divided by 2 is 55. So if you added 1 to 10, you'd get 55. All right. This one here says I'm going to take I equals 1 to n of some constant equals some number. Well, that means I'm adding a constant to itself n times. Well, that's just multiplication. That's what multiplication is multiplication is repeated addition. So we're adding c to itself n times, so this would be n times c. The rest of these are not as obvious. On the summation I equals 1 to n of I squared is just n times n plus 1 times 2n plus 1 over top of 6. Again, not very obvious. The summation I equal 1 to n of c times a sub I. Well, that's actually just, you can bring the c out. So you can bring the c out of a summation. If it's not part of the summation, it can be brought out. So if it doesn't have an I on it, it can be brought out of the summation. And that just makes some things a little bit easier because sometimes you can find the summation better. We'll do another one that's not real obvious. I equals 1 to n of I cubed. That turns out to be n times n plus 1 over top of 2 squared. And we already used this one. We already solved this one. But I just wanted to kind of tell you it's not an obvious one, but it is one that's formalized. We can prove these. Classes do this all the time. People, mathematicians, prove these all the time. Well, not all the time. They've proven them and they're done. We can prove them if you wanted to. The last one is the summation I equals 1 to n of a sub I plus or minus b sub I. This is just saying we're adding this summation or we're adding the sum or we're adding this difference. Remember, we can add in any order. So you can actually clump these together. So you can actually think of this as the summation I equal 1 to n of I sub a sub I plus the summation I equal 1 to n of b sub I. So you can add the a's together and the b's together. You can also subtract the a's minus the b's. So you can do either way. So we're going to use these a little bit to help us do some of these integrals while we're trying to do this. So we're going to do the integral from 1 to 6 of 2 plus 3x minus x squared. That is going to equal the limit as n goes to infinity of my function, which is 2 plus 3 times x I minus x sub I squared times delta x. And summation, I forgot my summation. Ooh, 1 to n. We want to find out what a little bit of the stuff is. So let's see what we can do with this. Let's see if we can find out what this delta x is. Well, remember delta x is defined to be the b minus a, your endpoints, subtract your endpoints divided by n. So in this case, your delta x is 5 over n. That means that my x0 is my first point. It's my starting point of 1. My next point would be 1 plus that 5 over n. My next point, x2, would be the 1 plus 5 over n, the x1 plus 5 over n. So notice it's 1 plus 2 times 5 over n. Notice I didn't write it as 10 over n. I want to see patterns here. I'm not trying to come up with exactly what it is. I'm looking for patterns. X of 3 would be the x of 2, 1 plus 2 times 5 over n plus 5 over n. So it's 1 plus 3 times 5 over n. I bet x4 is 1 plus 4 times 5 over n. You can try it and prove it to yourself that it is. You're just going to take x3 and add 5 over n to it, so you're going to get 4 over 5 over n, which means that my xi is 1 plus I times 5 over n. Notice it was x4, we had a 4 here, x3, we had a 3 here, x2, we had a 2 here. For that matter, x1, we had a 1 there. You just didn't see it. x0, we had a 0 there. Again, you didn't see it, but it was there. Which means I can now rewrite this a little bit differently. And this will equal we can rewrite our integral now from 1 to 6 of 2 plus 3x minus x squared Okay, so we want to find this integral. We now know that we can think of this as equal to the limit as n goes to infinity of my summation I equal 1 to n of 2 plus 3x sub I, but the x sub I we now know is 1 plus 5i over n minus x sub I squared, which we now know that x sub I is 1 plus 5i over n squared times delta x, but we know the delta x is 5 over n. All right, so now we have this. We have the limit as n goes to infinity of I equals 1, the sum of I equals 1 to n of 2 plus 3 plus 15i over n, when I'm multiplying this out, plus or minus, whoops, got my minus sign. When I multiply out 1 plus 5i over n and squared, I'm going to get minus 1. Then I'm going to get minus 10i over n, and then minus 25i squared over n squared. When you multiply it out, don't forget you're foiling this out. So you're going to take the square of the first term, multiply the outer and inner, multiply that by 2 because you have 2 of those, and then sorry, that's going to be what is minus. And then the minus signs all came from the fact that we had a minus out in front. Okay, times 5 over n. Now let's see if we can simplify this just a little bit. So notice I have a 2 plus 3 and a minus 1. And 2 plus 3 minus 1 is 4. So I'm going to have a 4. And then I'm going to multiply that 5n in. So let's go ahead. Well, we'll figure this out. We'll do the things first. We're going to have 4 plus, there's a 15i and a minus 10i. So that's a 5i over n minus 25i squared over n. And this whole thing is times 5 over n. Because the n doesn't involve an I, we can actually pull it out. It's just a constant, so we can pull it out. We can't pull it out of the limit, but we can pull it out of the sum. And we can also do the sum of each individual piece. So we're going to have the sum I equal 1 to n of 4 plus the sum I equal 1 to n of 5i over n. And we can do this because that one property that says we can. Minus the summation I equal 1 to n, 25i squared over n. Again, we can look at this summation. We're adding 4 to itself a bunch of times. So that's going to be 4 times about itself n times is going to be 4n. We're going to have 5i over n. We're going to pull that 5 over n out. Summation I equal 1 to n of just I. And the same thing here, we can pull that 25 over n squared. Got my square. Pull the 25 over n squared out, and then we just have I equals 1 to n of I squared. And then we look back and we see, what is this summation? We had that in our properties. That summation is just n. So we're going to have 5 over n, and then that's going to be the summation of I is, remember, is n times n plus 1 over 2 minus 25 over n squared, and the summation of I squared, remember that was n times n plus 1 times 2n plus 1 over top of 6. Okay. So far so good. We're getting things a little bit farther along. We're going to simplify this a little bit before we do the limits, but the summations are all gone. So that's kind of nice. Let's do a little bit of simplifying here. We have 5 over n times 4 over n. I'm sorry, 5 over n times 4n is 20. 5 over n times 5 over n times n plus 1 over 2. Well, these n's, I'm going to cancel here. And I'm going to have 5 times 5 is 25 times n plus 1 over 2n. And then I'm going to have, again, this n will cancel one of these. And we're going to have 25 times 5, which is negative 125. It's negative because of the negative sign there. We're going to have n times n, which is n squared. We have that 6, so we'll put a 6 in the bottom. And then we're going to have n plus 1 times 2n plus 1. Let's go ahead and multiply that out. That will be 2n squared plus n plus 2n is 3n plus 1. I was still not to where we can take the limit yet, but we're close. So we have 20. I'm going to go ahead and separate these up a little bit. These are too big the way they are. This is going to be 25n over 2n plus 25 over 2n. When I separate those out, that'll be kind of nice because now one of these n's cancel in this first one, so you're going to get 25 over 2 there. This one, again, multiplying and separating it out, we're going to get the 2 is going to go into the 6. So you're going to give a 3. The n squared is going to cancel. So a 3 in the bottom, a 125 in the top. The n squareds cancel. Minus 125. The 3 goes into 6 2 times. You can be left with a 2 in the bottom and an n in the bottom and 125 in the top. And then minus 125 over 6n squared. Okay. So now let's see if we can find the limit as n goes to infinity. Well, the limit of 20 as n goes to infinity is just 20. That one's easy. The limit of 25 over 2 as n goes to infinity is 25 over 2. That one's easy. The limit of 25 over 2n as n's going to infinity, 2 over n is going to go to 0. So this one's 0. We have the negative 125 over 3. That's going to be still negative 125 over 3. This one again has the n in the bottom. As n goes to infinity, the 2 over n, 1 over 125 over 2n is going to go to 0. Same thing with this one. This is an n squared in the bottom. So as n goes to infinity, this can become really, really small. So that's going to go to 0. So now what you do is just add 20 plus 25 halves minus 125 thirds gives me negative 55 over 6. Now, that's a really long process. We will find a quicker process, but I wanted you to get an idea that we are adding things together and doing these summations. Another example that I want to do is this one, the integral from -1 to 3 of 2 minus x dx. I'm going to do this one a little bit differently. One of the things I want to point out to you is that 2 minus x is linear. So we have lines, and we know how to find things when we have lines. So we're going to actually graph this. I'm going to go ahead and graph it in Desmos. So I'm going to bring up a Desmos. Trying to see if I have a Desmos. I don't have a Desmos open. All right. I mean, I had one, but not the one I wanted. So we'll go into Desmos. And we're typing 2 minus x. That was my function. And there's what it looks like. And if you remember, we're doing 2 minus x from -1 to 3. So I'm going to go over here and change my window here to let x start at -1 and come up here to x equals 3. That's all I really care about is from that range into that range. So this is what I have. I'm going to go ahead and grab this. And we're going to put this back where we are. All right, so here's our graph. Sorry, my picture's on there, but I didn't want to take the time to get rid of it. Okay, so here's my graph and here's what I have. And what I notice is I have rectangles. I have mostly rectangles here. Most of the way is rectangles, so I can do this. And so we're from -1 to 3. So from -1, we start here. This is area 1. From -1 all the way over here to 2, this is all above the axis. From 2 to 3, we're below the axis. We'll call this one area 2. We are going to figure out what these areas are and then subtract them. So this area is going to be, it's a triangle. Sorry, it's a triangle. And the area of a triangle is 1/2 the base times the height. So the base goes from -1 to 2. So that's 3. And the height is this height here. That height is going up from 2, that's 3. So it's a height of 3. So that area is 9/2. This area here, again, is also a triangle. So that's also the area of the base times the height. The base is 1. The height is also 1. I didn't call it -1 because we're just going to subtract the areas. So that's how we'll do it. But areas are positive, so we think of areas as being a positive quantity. So that's why I didn't subtract, do it a -1. But you can also do it that way and then add. It's up to you. But now what we have is we now have that my integral from -1 to 3 of 2 minus x dx is going to be area 1 minus area 2. Area 1 was 1/2, well, it was 9/2. We already figured that out. Area 2 is 1/2, because notice 1/2 times 1 times 1 is 1/2. And so 9/2 minus 1 is 8/2 or 4. Cool. So we now have that. We can do the midpoint rule, so we can take any point we want. We don't have to be the endpoints. We can do midpoints. So if we're doing summations, if we're actually going to do the Riemann sums, we'd actually find the midpoints. X bar is what we call the midpoint. It's half of the distance between x sub I minus 1 and x sub I. Again, your delta x is still b minus a over n. So we can do that. Again, you can use Desmos to do that, but you're just going to add those together. Last thing I want to mention are just some properties of integrals. These are really nice things that are true about all of our integrals. And so these are some nice properties that we have. The first thing is that the integral from a to b of f of x dx, that is actually equal to minus the integral from b to a of f of x dx. And the reason that is because your delta x is now negative because you went the other direction. That's the only reason. And they don't have to be, a doesn't have to be smaller than b. It's just that this is always a relationship. If you switch the limits of integration, then you put a negative sign there. The next one is that if I were to take the integral from a to a, means I'm not going anywhere. If I'm not going anywhere, then my delta x would be 0. So this is always 0. The integral from a to b of c times dx, that c can be brought out. And so you're adding up a bunch of your delta x's. So you're just going to have c. You're going to add up your delta x's n times. So you're going to have b minus a over n times n. So you're just going to have c times b minus a. The integral from a to b of f of x plus or minus dx, g of x dx, you can actually then just divide these up. So you can actually do this, the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Another property that's nice is that if you have a constant times a function, you can bring that constant out. So the constant, the integral from a to b of a constant times a function dx is c times the integral from a to b of f of x dx. So you can just bring that constant out of an integral. The last one is a very, very useful one that we like. There's actually going to be a couple more I'm going to do. Sorry, not the last one, but the one I want to do now is that it's a very useful one. And we actually kind of just used it. And what it says is that the integral from a to c of fx dx plus the integral from c to b of fx dx is the integral from a to b of f of x dx. C does not have to be between a and b. It's usually we pick a C that makes life just a little bit easier on us, but it does not have to be between A and B. It could be anywhere at all. All right. A couple other things I want to mention is that if your function is positive and A is less than B, then your integral will be positive. The integral from A to B of f of x dx will be positive, or greater than or equal to 0, I should say, because it's not always positive. All right. If f of x is greater than or equal to g of x and a is less than or equal to x is between a and b, then the integral from a to b of f of x dx is going to be greater than or equal to the integral from a to b of g of x dx. And you can actually understand what that means is if I have a function here, here's my f of x, and I have another function here, here's my g of x, and here's a and here's b, you can see that the area under f, which is that black area, is definitely always going to be bigger than the area under g, which is the green area. So you can see that this is going to happen. If m is less than or equal to f of x is less than or equal to big M, and a is less than or equal to x is less than or equal to b, then that means, remember, the integral of a constant is m times it's going to be m times b minus a. And that's going to be less than or equal to the integral from a to b of f of x dx, which is going to be less than or equal to big M times b minus a. Remember, this is just because you took the integral of each piece. So you take the integral of each piece, the integral of a constant is m times b minus a, and big M times b minus a. So that's just why it worked. So you just can take the integral of each individual piece. A couple more I just want to show you is if I happen to have the integral from 1 to 5 of f of x dx, and that equals 12, and the integral from 4 to 5 of f of x dx is equal to, let's say, 3.6, can I find the integral from 1 to 4 of f of x dx? Well, this is, again, that property that I think is very, very useful. And I'm going to just draw a picture of here to show you kind of what this looks like. I'm drawing in the first quadrant, nothing special about the first quadrant. Here's my function here. Here's 1. 2, 3, here's 4, and here's 5. So what I'm doing is I'm telling you that the integral from 1 to 5 is 12. And the integral from 4 to 5 is 3.6. So I'm telling you that the area from here to here, from 1 to 5, is 12. And this area is 3.6. Can you tell me what the integral is from 1 to 4? Well, again, this is very useful because I can do the integral from 1 to 5 of f(x) dx and subtract from that the integral from 4 to 5 of f of x dx. And because I can see that that's what I want this full area I have. I want to get rid of this piece, and I'm left with the piece I want. So this would be 12 minus 3.6. So that's 8.4. So you can use the idea of areas and just kind of think about what they do and what they're looking like. One more that I want to do is I'd like to find the integral from 0 to 2 of 1 over 1 plus x squared dx. I want to find out what that is. And in order to do this, I don't know what this is. I have no idea what this is. So maybe what I could do is find some value that 1 over 1 plus x squared is between on 0 to 2. So let's just think about, let's look at Desmos really fast. Let's look at the integral, let's look at the function, I should say, 1 over 1 plus x squared. All right, so there's my graph. I'm going to go ahead and go back to the home just to see a little bit more. And I look at this, and again, I actually want to do it from 0 to 2. So I'm only carrying from the integral from 0 to 2. So I'm only carrying what's happening there. So I'm going to go ahead and change my window to just go from 0 to 2. And what I have is I have this nice little function here looking like that. And that's what I have. And I noticed something very important. One thing I noticed is that 2 is up here. So this function is definitely less than 2. There's no way it could get bigger than 2 in this interval. It's always less than 2. And here we're greater than 0. So I now can tell you, I happen to now know that 1 over 1 plus x squared has to be less than 2, less than or equal to 2, and greater than or equal to 0. So I can use that property that tells me what it would be. And I can see that the integral from 0 to 2 of 0 dx is going to be less than or equal to the integral from 0 to 2 of 1 over 1 plus x squared dx is less than or equal to the integral from 0 to 2 of 2 dx. But we can now use the properties. Well, first off, 0, you're just adding 0 to itself a bunch of times, so you're going to get 0 there. So I have 0 less than or equal to the integral from 0 to 2 of 1 over x squared dx. And this integral, we can use that other property that tells us that the integral of a sum of a constant is just the constant times b minus a. So I have a constant times b minus a, and my b minus a is 2 minus 0. So I can now tell you that that integral, even though I don't know what it is, I can now tell you that the integral from 0 to 2 of 1 over x squared, of 1 over 1 plus x squared dx is between 0 and 4. I don't know what it is yet, but at least I have some idea of what at least is between. And those are some of the properties we have of integrals.